Okay, we're going to start with a little claim.
What's special about 1? When you multiply it by it, it doesn't do anything.
The matrix that acts like 1, the identity matrix, doesn't have all 1s in it. Because what I need is remember it's rows on the left times columns on the right. I need to only get A. So this is A plus no C's. And then the right column would be B plus no D's. And then on the bottom, I would have no A's, but a C, and then no B's plus a D. And that is not doing anything to the original matrix. So to show that two things are inverses, we want to get the identity matrix when we multiply, right?
Just like
the multiplication inverse of 3/4, for instance, gets me the multiplication one. Okay, so let's multiply these two things together. Again, rows, columns, getting used to that. Let's see. I'll just put it in the box. -2 plus 3, and then 3/2 minus 3/2. Well, that's good. And then the bottom row, you'll have 2 times -2 plus 4 times 1, and then 2 times 3/2 minus 4 times 1/2. Yay, life is good. Okay, so to find an inverse, I like to say, switch the diagonals. Switch the places of the diagonals, and then negate the antidiagonals.
Switch their signs, but don't move them.
Then divide by the determinant. So I like to do a little spade work first. Let's find the determinant. Okay, so we switch the diagonals. We change the signs on the antidiagonals. And then we divide everything by the determinant. There you go. Okay, so to solve using matrix inverses, if I write, the idea is first you write a matrix. I'm going to scrape out the numbers and put in x, y as a column matrix. Notice if I do the multiplication, that actually gives us what I want, 3x plus 5y, for instance. And then a little nice column matrix for this. Okay, so then the claim is x, y is I need to get rid of this matrix on the left. So another little note in color.
Pondering my variables. So different x.
Let's see. K times.
Home.
Yeah, I'll do it in one dimension. If I have a multiplication constant and the matrix on the left, that's a big constant. If I want to flip it to the other side, I need its inverse. So I will have 3, 5, -1, -2 inverse times 17, -6. And notice I already found the inverse because, note, that is the matrix from problem 2, and we just found its inverse. It came out to 2, 5, -1, -3. And remember, it's always, always, always rows with columns. So x is 2 times 17 plus 5 times -6, and y is -1 times 17 plus -3 times -6. Comes out to 4, 1. Wonder where that could possibly have come from. Take a look back at...
Oh, never mind.
Oh, no, that's a different one. Oh, never mind. Okay, so now let's try this next one. So the first thing I need to do is find the determinant. Oh, sorry, first find the inverse. Of the numbers from the left side. Okay, the determinant is -2. So we switch the diagonals. We switch the signs on the anti-diagonals and divide the whole schlimoli by the determinant. And we get positively has okay. So I have my original thing being 4, 2, 3, 1 xy being 2, 3, and then that means xy is that inverse. And I'm going to write it as a separate step so that you remember. Yes, there's an inverse button on your calculator for matrices. Remember, always, 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 rows on the left, columns on the right. -1 plus 3 is 2. 3 plus -6 is -3. If I write a system of inconsistent equations as parallel lines, when I try and intersect them, try and find the solution, there is no intersection. So if I did, for instance, 3x plus 2y equals 5, and 6x plus 4y equals 7. What happens when I try and find the inverse of 3, 2, 6, 4? The determinant is 3 times 4 minus 6 times 2. So you switch the diagonals, switch the signs on the anti-diagonals, and I have to divide by 0. You can't do it.